Okay, so let's look at another problem that is already given in the write-up of our lecture, and let's try to understand the problem itself. For example, here we have a mass m, and over that there's a disk of mass small m. This disk is rolling on top of the mass, so this bigger mass which is on the bottom is moving back and forth, and there's a disk that is on top of it which is rolling on top of it, right? So it also has a translation motion. The center of mass has a translation motion for the top one because the bottom mass is moving. In addition to the sliding, it is also rolling. So that the top mass has two motions. One is the sliding along with the small bottom mass. Second thing is rolling on top of the bottom mass. So there are two springs here. One is of spring stiffness K, one is of spring stiffness 2K. We have assumed that we have some kind of a frictionless surface, right? So like I said, this top mass not only has, this also has a translation, but it also has a rotation. So there are two things that are there, and the radius of that is said to be r small r, right? So we have the radius of the smaller mass, which is sitting on top of the bigger mass with capital M. So our goal is to write the equation of motion, determine the equation of motion for the two masses. So let's again use our Euler-Lagrange equation. So let's just remind ourselves our Euler-Lagrange equation. So, and we have also, second thing that we have is that we have some external force acting on the bottom mass. So last problem we did not have any external forces acting. Now we have some external excitation force that is acting on the bottom mass. That also we need to consider. But one thing we don't have any damping or friction, so we don't have any dissipative effects. So I can write my Euler-Lagrange equation as dou L by dou Qi dot minus dou L by dou Qi is equal to some Qi. So again, if we remember ourselves, L is nothing but our Lagrangian, which we defined as kinetic energy minus potential energy. So kinetic energy or potential energy. Then we define L as our Lagrangian. So then we said Qi is nothing but our generalized coordinates. And Qi is nothing but our generalized forces. We have not used generalized forces so far. In this problem, we'll try to use our generalized forces as well, so that we are able to talk about some new concepts as we go on. Another thing is we have not yet defined what our generalized coordinates are. For the bottom mass, let's say, that's our bottom mass, things are reasonably simple. We can say the bottom mass is moving in this direction in a linear fashion. But our top mass, it's moving linearly together with the bottom mass, but it's also rotating. So it's more convenient to use a theta. For example, when you have our pendulum problem, we had a theta. It's more convenient to use theta because we also need to account for the rolling motion. So let's say our generalized coordinate is phi. Right? So, and we can, since we have this, so then we can write our potential energy. So it's much more simpler, right? So our potential energy is, why is the, okay, before we go into writing our potential energy, let's think of our kinetic energy. So we have one term coming because the lower mass is moving. So right, that's pretty straightforward. Half m into x dot square. Now second thing that is coming in is the center of mass of the disk is linearly moving along on with the top mass. Right. So we can say half m into v square. We'll come to that in a second. We also have the rotational motion, kinetic energy because of the rotation motion. So half into moment of inertia or into phi dot square. This is nothing but half m r square. Right? So if you go into earlier structures module or dynamics module, this is something that we would have talked about either in mechanics in year 1 or dynamics in year 2. Right? So this is something that we are taking from either the mechanics in year 1 and also dynamics in year 2. I would kindly request that you go and revise how, if there's a rotational motion, how do we write the kinetic energy from one of these modules. For now, let's assume that you already know that, and we are going to use these terms. So the second thing we have not defined is our velocity. So we can define our velocity, or linear velocity to be more precise, of the rotational object. Again, this is something we would have discussed in mechanics or dynamics. So you can say, right, V is nothing but x dot, which is the motion of the bottom mass, minus r into phi dot. That is nothing but gives you our linear velocity of the linear velocity of the center of mass of the rotating mass on top. Okay. So now we have written our kinetic energy. Similarly, we can write our potential energy from the spring. So one spring is reasonably straightforward. We have half k into x dot square. Sorry, x square. Okay, so half x square. That's coming because of the spring here. So there we have one spring here. So half k into x square. Second spring we have here is a spring because of with the spring constant of 2k. So there the displacement is half into 2k into r into phi. That is our linear change in the distance whole square, right? So that would be nothing but half kx square plus 2k, sorry, k into r square into phi square. Okay. So your two terms are related to our kinetic energy and our potential energy. And now we are going to go and write our Lagrangian, which is t minus u, and we are going to get each of these terms of the Lagrangian. So I say x dot. So I have not written our generalized forces yet. We'll come to that in a moment. And this side we need dou L into dou C dot. I'm just going to write some of these terms. So we know that dot or velocity term would come in from our kinetic energy. So we can write m into x dot, right, plus m into x dot minus r phi dot. Okay. So similarly, we write the kinetic energy, m into minus r into x dot minus r into phi dot plus ic into phi dot, right? Or I can just remove these negative signs here and just cleanly write it out here as minus m into r, right? So I can easily write out these two terms as m into r, and that makes my life more easier when I have to write things out. Right? Okay. So now I can further again write the second term as d by dt L by dou x dot is nothing but m into x double dot plus m into x double dot minus r into phi double dot. Similarly, d by dt by dou c dot is equal to r into x double dot r phi double dot plus ic into phi double dot. Or I can rewrite this as minus mr x double dot plus mr square phi double dot plus 1 by 2 mr square phi double dot. Or I can combine these two terms and I can basically write mr x double dot plus 3 by 2 mr square phi double dot, right? Similarly, I can write the last term that we need, or we still need the generalized forces, or so dou L by dou x and dou L by dou phi, right? So I can get these terms from my potential energy. This is nothing but k into x, and here I have k r square, or 2k r square into phi. Last thing I need is the generalized forces. So we have not used the generalized forces so far. So we need the generalized forces. So we can say, what is the generalized force? It is nothing but, let's say, if there's a work force that is moving the object in some distance delta x or delta phi, then that's adding some kind of potential energy, right? So we can say, let's say, some change in potential energy or let's say we can call this as, let's say, some work done by the forces, to be more accurate, is equal to some delta q in x, which is moving the object in delta x in the x direction, some delta very small, plus delta q in phi into delta phi, right? So there's no force acting in q direction, so it's nothing but f of t into delta x, right? So, or we can say, let's say, to be, sorry, my mistake here, so this should be not delta but qx and q phi, you know, that is nothing but our generalized force. Here it's a very, very simple form where the force is acting in the direction of motion, but this could also be a force acting in not in the direction of motion, then it's more complicated. But for the purpose of this module, we'll consider generalized forces that are acting in the direction of motion, so things are a lot more easier to think about. So let's start to collate all the equations together. So we have, so let's say we have all these terms. I'll try to start putting them together. So let's say we take these terms, copy, or maybe I'll just write it out so it's more easier. So for mass m and for mass m, I have m into x double dot plus m into x double dot minus r into phi double dot minus of minus kx equal to 0. So that gives me m plus m into x double dot minus mr into phi double dot plus kx equal to, sorry, it's not 0, there's a force f of t acting in the x direction, f of t. Similarly, for the rotational motion of the top mass, I can write this as, I'm just copying so that I'm correct. To be right, 3 by 2 mr square phi double dot minus mrx double dot sorry, just to make my mistake here, so Lagrangian there has to be a minus here. To phi. So just please note that mistake. So there needs to be a minus here when I was solving. Like I said, there's again a mistake that I can also make, like you would also probably could make in the exam. Our Lagrangian is kinetic energy minus potential energy. So when you're taking these derivatives with regard to the terms that are in the potential energy, this minus is very important to note. That's kind of where these minus signs come from, that I missed probably when I was writing last time, right? So yeah, so just to be careful there. So I got this correct here, but I missed it in the when I was writing previously. So just that's something to note there. Minus 2k r square phi equal to 0. So there's no force acting in the theta direction. So if I rewrite this, mr x double dot plus 3 by 2 m r square phi double dot plus 2k r square phi equal to 0. Okay. So these are the two equations of motion that we get.